enzymes that pass through the membrane. Both of them are modified with sugars, highly glycosylated, and they also are molecules which, even under the best of circumstances, have difficulty getting folded in just the right way so that the quality control within the cell says, yeah, this looks right, you can pass it on. And so if you look at those half-lives of systems, CFTR, for instance, about 70% of it gets degraded within the ER and never gets released. And it's because it has such a difficult time energetically folding. NPC1 is very similar. I'd say about 50% of it is degraded. So if it turns out that the machinery within the ER and that is used for folding CFTR and folding NPC1 has an overlap, then it may be that some of the small molecules that are effective for CFTR might be effective for NPC1. And what I did show you before with the correctors, C1 and C2, well, both of those correctors were developed for CFTR. So those did have some degree of.
Have you tried the Vertex?
After a lot of work, I have succeeded in getting my NTA signed with Vertex.
Okay.
I had to sign away my first child and basically give away intellectual property in order to get it done. But yes, we have the compound, and we'll be able to test that in the next few months. What I'm hoping is that we can work with the Vertex scientists, because it may be that this is, VX809 is good, but they may have better ones that they have developed along the way. And of course, it will be very important that whatever corrector that we look at would be one which would be able to cross through the blood-brain barrier. And so, it's possible that this may be a starting point for a chemical scaffold that could be then modified through medicinal chemistry to get something that is appropriate for NPC. Okay. Well, now I'm going to let Laura take it from here, and then after Laura, we'll have Denny speak.
Thank you very much. Thanks, Dan. And thank you, Karen, for giving me the opportunity to speak and for letting Ronnie introduce me. When Ronnie was on the staff at Tufts, she provided the sunshine for our department for many years. And it's been a cloudier place in Boston without her. It's nice to see her again. So I'm Laura Liscombe, and I'm from the Department of Physiology at Tufts in Boston. And today I'm going to tell you about some relatively new work that my lab has been conducting. Most of my career has been spent looking at NPC in cultured cells, in fibroblasts, in Chinese hamster ovary cells, in many types of cell models in which exhibited a Niemann-Pick phenotype. And it's only recently that we've begun to go to a mouse model. So today I'm going to tell you about some of the new mouse models that we have developed that express NPC liver disease and neurodegeneration. And the objectives of the work that I'm going to describe were, first of all, to be able to turn NPC disease on and off when we desire. And I'll be explaining what I mean by these various objectives. We wanted to be able to evaluate the effect of modifying genes on the disease progression. And we wanted to be able to observe the ability of a sick mouse to recover from NPC disease. Because we're all hoping, as Dan described, that someday there will be a therapy for NPC. And most likely that therapy will be applied to an individual after they are affected with the disease. And how well does an affected individual recover from the release of all of that stored lipid? Now, we created this mouse model by treating mice with a molecule that's called an antisense oligonucleotide. Now, an oligonucleotide is just a short bit of DNA. And this little bit of DNA, I think, is pretty miraculous. We can put this bit of DNA into solution and inject it just under the skin, into the abdomen. And it finds its way around the body. And these oligonucleotides, or bits of DNA, are modified such that they are taken up primarily by the liver cells. And so that's why we began our work looking at NPC liver disease. They are called antisense because the genes in every one of our cells are making bits of that nucleic acid is making a bit of RNA that will produce a protein. And that bit of RNA has sense. It's called the sense strand. These antisense oligonucleotides, when they get into the liver, they're taken up by all of the cells of the liver, and miraculously, again, through all of the gumbo there that's inside the cell, these antisense DNAs find the sense bit and bind very tightly to it and prevent it from doing its job. So here we're looking at a nucleus of a cell, and the genome there has got all of the normal DNA in this cell. It's making a bit of sense RNA that leaves the nucleus and normally would be translated into a protein. So if this was an RNA that was destined to become NPC1, it would get translated and an NPC1 protein would be made. If the cells have got this antisense bit of oligonucleotide in them, there's a very tight binding, and now this RNA can no longer be translated. And so what we have here is a cell that is now unable to make NPC1. So the sense strand codes for protein. This antisense is complementary and prevents the sense strand from doing its job. And so what we are expecting is that if we take a normal mouse and undergo these injections, that we will make a mouse that is now sick with NPC disease. We treat our sick mice very carefully in the mouse colony. So in our first experiments, we injected the mice twice a week with these antisense oligonucleotides, and one of them was designed to latch onto NPC1 and prevent its production, and the other one was a scrambled version of that nucleotide that would serve as a control, and we would expect the mice not to get sick if they were injected with the control. And we carried out those injections for 2, 4, 6, and 9 weeks. Now, we weren't quite sure what to expect. How quickly would this antisense achieve its goal of knocking down NPC1 protein? Now, you can imagine, if you will, if we block production of an object or a molecule, very quickly it might disappear from our existence. For example, if Tim Hortons decided to stop production of their donuts this morning, there would be a run on Timbits, and by this evening there would not be a Timbit to be found across Canada, because I've seen the lines at Tim Hortons and the people eating those Timbits. They go over very quickly. So they are a product that is made and gets used up very quickly. Now, contrast that with another product